This program will provide the viewer a basic understanding of carbon adsorption processes used to control air pollution and the control devices under this category. We will cover what are the two types of carbon adsorbers, those that regenerate on-site or off-site, and their characteristics, proper operating conditions, which includes temperature and pressure and other parameters, also causes of decreased performance and performance monitoring. In adsorption processes, gaseous contaminants are removed from a gas stream by transferring them to the surface of a solid adsorbent. These adsorbent materials include silica gel, activated alumina, molecular sieves, polymers, and activated carbon. The most common material for the adsorption of organic pollutants is activated carbon. A properly designed activated carbon system is generally capable of removing 95 to 98% of an organic contaminant. There are two types of adsorption processes: chemical adsorption and physical adsorption. Chemical adsorption is not used often in air pollution control systems because of the difficulty in regenerating the adsorbent material. In physical adsorption, the contaminant molecule is lightly held to the surface of the absorbent by weak electrostatic forces, and the adsorbent material can be easily regenerated. There are two types of activated carbon systems, those that regenerate on-site and those that do not. The two most common industrial adsorbers are a fixed bed design that regenerates on-site and a fixed bed design that does not regenerate on-site, often referred to as a carbon drum. Today we will be seeing units of both types. The amount of material adsorbed by activated carbon is termed its retention or capacity and is expressed in weight percent or in pounds of organic contaminant adsorbed per 100 pounds of carbon. There are several types of capacities, and they all depend on the operating conditions and on the particular organic contaminant being collected. Saturation capacity is the maximum amount of organic material the carbon can hold. Breakthrough capacity is the amount of organic material the carbon can hold before significant organic concentration begins to exit or break through the carbon bed. Heel capacity is the amount of organic material remaining in the carbon bed after it has been regenerated. Working capacity is the difference between breakthrough capacity and heel capacity and represents the amount of organic material that can be adsorbed in each operating cycle. A typical working capacity is 10 to 20 pounds of contaminant per 100 pounds of carbon. The ability of activated carbon to retain organic contaminants is influenced by a number of parameters, including temperature, pressure, contaminant concentration, contaminant molecular weight, and the presence of moisture and particles in the gas stream. At lower temperatures, the retention of the organic contaminant is highest. Because of this, carbon adsorbers are usually operated at temperatures less than about 125 degrees Fahrenheit. The low retention at higher temperatures provides one method for regeneration. At lower system pressures, retention is lower, providing another method for regeneration. Retention also increases as the organic concentration increases. However, more total carbon is usually needed at higher concentrations because of the greater quantity of organic contaminant that must be collected. Retention is affected by the molecular weight of the contaminant molecules. As the molecular weight of the molecules increases, retention increases. Moisture in the gas stream can also affect retention. Water will adsorb onto activated carbon, competing with the organic contaminant for adsorption sites. Since adsorption is also affected by the presence of liquid and solid particles in the gas stream, particulate matter must be removed before entering the adsorber. To review, the common types of activated carbon adsorbers that capture air pollution regenerate on-site or off-site. Carbon adsorption systems have retention capacity that includes the heel and breakthrough capacity. Between these 2 points is the working capacity. The saturation capacity is the maximum amount of organic compounds the carbon bed can hold. Retention can be affected by temperature, pressure, organic concentration, contaminant molecular weight, moisture, and any particulate matter in the system. There are several factors that contribute to the loss of performance in an activated carbon adsorption system. These problems include corrosion of the carbon bed support and subsequent collapse of the bed, infrequent desorption, loss of capacity due to the accumulation of condensed organic material, plugging of the activated carbon bed with particles, physical deterioration of the carbon granules, increased operating temperature, increased organic vapor concentration. The ability to evaluate potential problems during a field inspection will depend on how well the system is instrumented. Most large activated carbon systems are well instrumented. However, smaller systems may have limited instrumentation. Performance evaluation of these systems will be difficult unless measurements of important parameters are made. There should be 2 goals in any field inspection. First is to evaluate the source's compliance with any rule-specific monitoring requirements and with the provisions of the Title V permit. In addition, parameters that influence performance should be evaluated to see if there are shifts from their baseline values that could indicate reduced control device efficiency. The most direct measure of the performance of an activated carbon adsorber is the organic vapor concentration in the outlet gas stream. Active adsorption occurs in a thin mass transfer zone that moves down through the carbon bed until the breakthrough point is reached. If breakthrough is occurring, the outlet concentration from each bed will be highest just before it's regenerated. If there is a permanently installed analyzer, the adequacy of the data should be checked as part of the overall performance evaluation. This would include an inspection of the condition and integrity of the sampling system and a check of the sample gas flow rate. In addition, the calibration frequencies and procedures in the maintenance records for the instrument should be checked. Calibration should be performed on a daily basis using a calibration gas cylinder that is less than 6 months old and has a pressure of at least 150 psig. If there is no permanently installed analyzer, the concentration measurements will have to be performed with a portable analyzer. Due to the limited pump capacity of these analyzers, measurements must be made in the portion of the outlet ductwork that is under positive pressure. If the adsorber is regenerated using steam, measurements should not be taken when the adsorber is in the purge cycle. The purge cycle begins after regeneration is completed and is used to dry the carbon bed and cool it down before it is put back online. During this period, water droplets and high humidity are present, and this moisture can damage the instrument sensor. Both permanently mounted and portable analyzers can provide an accurate indication of the outlet concentration when they are calibrated for the specific compound or compounds present in the gas stream. Often, outlet concentration measurements required by regulation are based on calibrations with a reference gas. The instruments are calibrated using a readily available organic compound such as methane, propane, hexane, or 1,3-butadiene as specified by the applicable regulation. Under these conditions, the instruments will provide a measure of performance relative to a compliance limit expressed in units of the calibration compound or as carbon. The inlet concentration to the carbon adsorber should also be checked. Adsorbers designed to operate at 10 to 25% of the lower explosive limit will usually have an LEL monitor in the inlet duct to shut the system down if the concentration increases above this safety limit. Otherwise, the measurement will have to be made with a portable analyzer. Increased inlet concentration could lead to breakthrough unless the regeneration frequency has been increased. The inlet gas temperature is one of the most important variables affecting performance. Increased gas temperature will substantially reduce the capacity of the carbon bed, leading to breakthrough. The current inlet gas temperature, and if it is being recorded, the temperature over the last several months should be evaluated for significant increases above baseline values. The pressure drop across the carbon bed should be evaluated. As the carbon bed ages, it settles and compacts, causing the pressure drop to increase from baseline values. Since old carbon may have less capacity than new carbon, an increase in static pressure drop may indicate reduced performance. An increase in the pressure drop can also be caused by accumulation of particulate matter on the inlet side of the bed. The blinding of some of the carbon granules together with poor gas flow distribution will cause increased emissions. Decreased pressure drop is usually due to partial or complete collapse of the fixed bed because of corrosion of the support grid. This will also cause increased emissions. Gas flow rates above the design range of the adsorber can potentially lead to breakthrough. An increase in the gas flow rate is indicated by increased fan motor current, increased adsorber pressure drop, and increased hood static pressure. Decreased gas flow will result in reduced capture of the contaminants at the source, resulting in fugitive emissions. A decrease in the gas flow rate is indicated by decreased fan motor current, decreased adsorber pressure drop, and decreased hood static pressure. The regeneration frequency and cycle time should be compared to the baseline values. Decreased regeneration frequency and time can reduce the capacity of the carbon bed, leading to breakthrough. If information is available, the quantity of recovered organic material should be compared to baseline values. If the quantity of organic vapor entering the adsorber is constant, a reduction in the amount recovered indicates reduced collection efficiency. If the quantity of recovered organic contaminant is monitored, a material balance can be used to evaluate the performance of the adsorber. With this approach, the quantity of organic material recovered over some time period is subtracted from the quantity of organic material used in the process during the same period to determine how much contaminant was lost to the atmosphere. Finally, the physical condition of the adsorber system should be evaluated. Corrosion of the adsorber vessel and ducts can be caused by the formation of acid compounds in portions of the unit. The most common areas of corrosion include the bottom of the vessel, where liquids can accumulate, and the outlet ducts, where moisture is present during the purge cycle. To determine that a carbon adsorber system is working efficiently, field personnel should observe, if possible, the organic vapor concentration in the inlet and outlet gas streams and the method used for its monitoring. Inlet gas temperature, the pressure drop across the carbon bed, gas flow rates, and regeneration frequency and cycle times. The inspector should always be aware of the air pollution sources need to be in compliance with applicable rules and to observe the source's records and the control device's physical condition. Carbon adsorption systems used for air pollution control have many safety considerations, including inhalation hazards, high-temperature steam. Further training and experience will be necessary to complete all field tasks safely.